All right. All right, welcome everyone to another Talk Math with your friends. It's my pleasure to introduce today's speaker. Daniel Litt is an algebraic geometer from UGA, and he is well known on Twitter as an aggravator of graduate students and a defender of the pseudo-theorems. And please join me in welcoming Daniel.
Thank you so much for that introduction, Ken. It's really nice to be here. So I want to tell you about what is a polynomial, and I want to start with some fairly elementary stuff, just like discussing literally what is a polynomial, and then we're going to get to sort of some of the geometry and arithmetic that I find really exciting about polynomials. And here at the bottom, I've drawn an addition symbol and a multiplication symbol, and they're friends. And hopefully we can join them as friends by the end of the talk. Okay, so what's a polynomial? So the first way you can think of a polynomial is as a formula. It's like literally just an algebraic object. So can some people type some of their favorite mathematical constants into chat, or unmute and say them? So I is a constant, great. So I, let's make our polynomial I times x squared plus 14xy plus is tau 2 pi. Sorry, I can't bring myself to write tau times, let's see, z to the 7th plus, okay, e to the 2 pi I over 7 times xy z to the 5th. Okay, so that's an example of a formula. It's a polynomial, and here notice it's a multivariable polynomial, and its coefficients are complex numbers. So here I is a complex number, and e to the 2 pi I over 7 is a complex number. And if I had room in this little red blob I'd add, I would add Brian's number, 1 plus square root 5 over 3 times some other variable. Okay, so this is the kind of algebraic object that's at the heart of this talk. Okay, so you can view this object as a function, right? So here, if you have 3 complex numbers, f, x, y, and z, you can plug them into f, and that gives you a map from, c cubed, triples of complex numbers, to c. Okay, and if I had more variables, you would get a function with more inputs. Instead of c cubed, you might have had c to the billion, and you would still get one output. So this is how you go from a formula to a function. Sorry, this is maybe review from calculus 1 or from pre-calculus or something, but I think both of these points of view are equally valid, and I want to stress that. Like, there's in algebraic geometry, we care about the algebra as well as sort of these functional pictures. Okay, and then if you have this function, you can look at the set of solutions, f of x, y, z equals 0, right? And so that's an algebraic variety, the set of solutions. So oops, I've lost my fill in the blank here. So the set of solutions here, so the set of x, y, z, such that f of x, y, z equals 0 is what's called a variety. So variety. And maybe just as an example, if I took the equation y squared equals x cubed, let's say just y squared equals x cubed, and if you graph the real solutions to that would look something like this. It would be, this is called a cuspidal cubic. And if you could also graph like the complex solutions, and then it would look something like this. It would be a sphere with a little point. It would look kind of like a teardrop. Okay, and so this is, we have a geometric object, a shape, we have a function, and we have a formula. And what I want to talk about is the interplay between all of these things. So the way I like to think about polynomials is not as any of these things, but actually as a bridge. So in particular, I want to explain how the sort of algebraic nature of a polynomial, which is related to arithmetic, like adding and multiplication, influences geometry. So in other words, what's special about polynomials? Here we have a formula or a function or a shape. What's special about the shapes or formulas or functions that show up this way? And someone is saying that they don't have a favorite shape. Hopefully you'll have some favorite shapes by the end of this talk. All right. So anyway, I want to explain this bridge. I want to explain how to go from arithmetic. And really, when I say arithmetic, I mean not just adding and multiplication, but like number theory, actually. Like so sort of questions you might ask about arithmetic, which is what I would say, that's how I would define number theory, is like, what are the questions you can ask about arithmetic and what are the answers to those questions? And I want to tell you how those number theoretic things influence geometry. All right, so let's start with a warm-up. So this is an old result of Serre, which in fact we can almost completely prove in this talk. So this is more or less the only thing I'm going to really prove in the talk, but I think it's really fun and absolutely beautiful. So okay, so suppose I'm given a bunch of polynomials. Like, so f here is, I'm going to think of as a map from n tuples of complex numbers to n tuples of complex numbers, and it'll have a special shape. So it'll be given by n polynomials in n variables, right? So how do I go from a formula like this, like, so n polynomials in n variables? Maybe let me say that they're actually polynomials. So this is in the set of polynomials in n variables, and this is in the set of polynomials in n variables. Well, if I have n polynomials in n variables, I can plug in numbers for the variables and get n numbers out, right? And I'm going to make an assumption. I'm going to make the assumption that if you do this twice, if you compose f with itself, you get the identity. So if you stick some numbers into f, you'll get some new set of numbers. Then if you stick those into f, you get the ones you started with. Okay, so this is called a polynomial involution. Involution just means if you do it twice, you get back to where you started. Okay, and what did Serre prove? So Serre proved that if you have a polynomial involution like this, it always has a fixed point. So I want to explain how to prove that. It's not at all obvious, I think. So let me, maybe before proving it, let me give you a couple examples of polynomial involutions. So here's one. You could take, here this is, n is 1. So I want one polynomial in one variable, and I'll send x to 1 minus x. Okay, and that has a fixed point. What is it? It's like x is 1/2, right? 1/2 minus 1/2 is 1/2. All right, what about this one? So this, if you really like doing algebra, or you have a computer algebra system available, you can check that this is a polynomial involution. I came up with it. It looks a little bit more complicated. Here, this has degree 9. If you look at it, there's a 1 minus y minus x cubed, and then you're cubing it. But nonetheless, I claim that if you plug this function back into itself, you'll get xy. So this is an involution, and if maybe a fun challenge if you want to think about it a little bit is, how do you actually generate interesting polynomial involutions? It's not so easy. So maybe let me just tell you the trick that I used to make this one. So what I did is I set a of xy to be xy plus x cubed. So this is an invertible map. So the inverse is given by a inverse of xy is given by xy minus x cubed. And then I took b to be a very simple involution, and took b to be 1 minus xy. B of xy is 1 minus y, 1 minus x. And then this f is what you get by taking, I think it was a inverse composed with b composed with a. So if you take a conjugate like this of an involution, you get an involution. And it's in fact, okay, so this is a fun way to generate complicated looking, but not actually complicated involutions. But in fact, it's an open problem, whether if you take a finite order polynomial automorphism, whether it's always conjugate to a linear one like this. So we don't even know if this kind of construction gives you out everything. So proving something about all polynomial involutions is kind of challenging because we don't have any kind of nice classification. All right, so I want to explain the proof of this this sort of warm-up result. And maybe unsurprising, it's going to have something to do with arithmetic. But before we do the warm-up, or before we do the warm-up to the warm-up, even, we're going to have to do a warm-up to the warm-up to the warm-up. Okay, so this here is a theorem I want to prove with you together.
Is it obvious what the fixed point is of that example so far?
I'm sorry?
That you claimed the first example was an involution, but were we supposed to know what the fixed point was?
Oh, in this example?
Yeah.
The second example? So in the first example is 1/2. In this one,
yeah.
What you would do is you take 1/2, 1/2, and then plug it into a inverse, I think, to get the word. So I think it would be 1/2 and then 1/2 minus 1/8. So 1/2 3/8 is probably the fixed point. But yeah, I would have to think about it.
Okay, thanks.
Yeah. But
Doesn't every involution of the form you described have a unique fixed point?
no. So for example, you could take the involution like x comma 1 minus y, and then x comma 1/2 would be fixed for any x.
Yeah, okay.
So what's true, and we'll see this in not too long, in fact, is that if the set of fixed points is finite, there's always an odd number. Okay. Okay, so let's start with a warm up to this warm up, or a warm up to the warm up to the warm up before. So here this is the key lemma to prove the theorem we just proved. So suppose you have a finite set and it has an odd number of elements. Okay, so here I've drawn for you a set with 13 elements, labeled 1 through 13. And here's my claim for you. So suppose I have a map from this set to itself, which is an involution. So if you apply the map twice, you get the identity. Then I claim this map has a fixed point. Okay, so let's prove it. Well, I'll kind of prove it pictorially. So let's make an involution, right? So where should 1 go? So someone type a number in chat, please. So 1 should go to 3, great. Okay, and then 3 has to go to 1, right? Because you need this to be an involution. Great. Someone typed 4, so let's send 2 to 4. Okay, and then 4 has to go to 2. And then someone typed 10, so let's send, we already have 3 and 4, so let's send 5 to 10. Great, and then 10 has to go back to 5. And let's send 6 to 7, because someone typed 7 in the chat. Great. Where should, okay, so a bunch of people want 8 to go to 13, great. And then, so I need one more number, 9, 10, or 11 or 12. Where do you guys want 9 to go? Okay, 9 should go to 11. Okay, and
obviously 11. Turn it all the way up to 11.
I'm sorry?
Who's that? This is Spinal Tap reference, sorry.
Oh, yeah, we're turning the talk up to 11. Yeah, so that means that 12 has to go to itself. Okay, so what's the proof? Well, what we proved is that the involution pairs up elements of our set, right? It divides them into sets of order 2. But when we do that, our set is odd order, so there has to be something left over, and that's 12. So the proof is that if we have an involution, it divides our set into sets of size 2. But if we have an if we have a set of odd size, that means there has to be something left over. Or in general, what this tells you is that there's an odd number of fixed points, right? The set of non-fixed points has even size because it's a disjoint union of sets of size 2, right? Are there any questions about this warm up to the warm up to the warm up? Great. All right, let's relate this to polynomials. So let's do the warm up to the warm up now. So here's the warm up to the warm up. So now suppose you have an odd prime number. And what we're going to do is we're going to prove a version of Serre's theorem. So a version of this theorem about polynomials having a fixed, involutions, polynomial involutions have a fixed point, not over the complex numbers, but over a finite field. So let me just remind you what a finite field is. So here, I'm going to take the finite field, fp. So this is what you get when you take the integers, you divide by the prime p, and you look at the possible remainders. And those are things that it makes sense to add and multiply. And every non-zero element has an inverse, so this is a field. And what we're going to do is we're going to look at polynomials with coefficients in this field. So suppose I have n of those, so n polynomials with coefficients in the finite field. So the coefficients, if you'd like, are residue classes mod p. And suppose that these n polynomials satisfy, again, the property that if you compose them with themselves, you get the identity map. So you get the polynomials x1, x2, x3, x4, x5, x6, up to xn. So then you get a map that you can view this set of polynomials now not as a map from Cn to Cn, but as a map from Fp to the n to Fp to the n. So given an n tuple of elements of Fp, you can just plug them into your polynomials, right? And you get another n tuple elements of this finite field. So the claim is just like in Serre's theorem. If you have one of these maps, which when you compose it with itself, you get the identity. So when you apply it twice, you get back to where you started, then it has a fixed point. So can anyone tell me why this is true? So the observation is that fp to the n.
Cameron says p to the n is odd.
Yeah, exactly. The number of elements is odd. So we're exactly in the situation of the previous slide. So we just proved an involution of a set of odd order has a fixed point. So really, in fact, we didn't really use that our map came from a polynomial. We just used that it was a map, right? Cool. Are there any questions about that? Great. All right, so now let's do the warm-up. Well, we can't quite do the warm-up, but let me remind you what we're trying to prove, and then we'll get to the warm-up. So remember, we had some polynomials over the complex numbers, in particular the complex coefficients. We assumed that when we applied these polynomials to themselves, we get back to where we started, and we wanted to show that we had a fixed point. So let's make a simplifying assumption. Rather than assuming these polynomials have complex coefficients, let's assume they have integer coefficients. Okay? So now what can we do? Now we can reduce mod p. So we can reduce mod of prime p. In other words, we can take these polynomials, take their coefficients, look at the remainder when you divide by p. That gives us some some polynomials with coefficients in a finite field. And what do we get? We get a fixed point mod p for every p. For all p. Okay, so now what we can do is let's look at the set of fixed points. So let's look at the set x1 through xn such that f of x1 through xn equals x1 through xn. So this is an algebraic variety, right? It's the set of solutions to a polynomial equation, or a system of polynomial equations, really. And what we know is that this is non-empty mod p for all p, or for all odd p, really. So we know that this is non-empty mod p for all odd p. Okay, now it's not totally obvious, but this implies that that it's non-empty over the complex numbers. And if you'd like, this is a consequence, for example, of the null-Stellen-Satz. But there's a lot of ways to prove this. So the claim is that if you have a set of polynomials with integer coefficients, which has solutions mod p for almost all p, or for infinitely many p even, then it has to have solutions over the complex numbers. And Joshua mentions the Grothendieck theorem, which I'm going to get to in a little bit. All right, so we had this simplifying assumption, and to me this really feels like cheating, right? Like we got ourselves into a solution where we could reduce mod p. So of course we reduce mod p, right? But what if we had some weird polynomials? Like what if they weren't integer coefficients? So here I gave you an example. So what if f of x is like pi minus x? You can't reduce that mod 5, right? What is pi mod 5? Or here I wrote, what if f of x is e minus pi times x cubed plus the Euler-Mascheroni constant times gamma plus some other stuff, and then y to the 7th minus Chaitin's constant times x cubed times y plus blah, blah, blah. So you could have a polynomial like this. There's nothing stopping it from being an involution. So what do you do in this case? So like, what does the arithmetic have to do with things over the complex numbers? That's what I wanna get at. So like in this weird situation, like what do you do? And what you do is you use the following observation. And to me, I think this is like one of the most beautiful observations in all of like mathematics. So you use that there are finitely many coefficients. So let me say what I mean by that. So suppose you have your finite set of polynomials, so f1 through some big number fn, maybe a billion polynomials, and they're polynomials in m variables, where maybe m is a trillion. So no matter what set of polynomials you have and however many variables, you only get finitely many primes. You only have finitely many coefficients, right? Sorry, I don't know why I said primes there. So you might as well work over the subring of the complex numbers generated by the coefficients. Right, this polynomial has coefficients in this ring, z adjoin the coefficients. So maybe that's z adjoin pi and e and the Euler-Mascheroni constant and Chaitin's constant and 1 over a billion and 1 over 7 and whatever you'd like, e to the 2 pi I over 7 someone gave me earlier. But this ring is something which you can take and reduce mod p. So here you can map this ring to finite fields. So if you have a map from this ring to a finite field, and you have a polynomial over the ring, you get a polynomial over the finite field. You can also, by the way, do other arithmetic stuff too. So for the experts in the audience, you can do things like embed in a p-adic field and do all kinds of other fun stuff. Okay, and now that we're in this situation, so we now have this ring which we can reduce mod p or whatever you'd like, you can just use exactly the same proof from before. So we've now proven this theorem about polynomials with arbitrary complex coefficients like e and pi and whatever using reduction mod p. Okay, modulo a little fact from algebraic geometry. Okay, so just a remark. I mean, I love this proof. I think it's really cool. It's not the strongest thing you can prove. So in fact, this fact, if you have an involution of Rn or Cn, in fact, it always has a fixed point, even if it's continuous. So actually, this theorem is true for continuous maps. And that's much more non-trivial. So one really needs some kind of fancy techniques to prove that more general theorem. Okay, so now I want to give you an example, something special about polynomials. So I want to tell you how to use this kind of method to prove, well, I think what Joshua mentioned in the chat, the Grothendieck theorem. So here's the theorem. So just like before, suppose we have an n-tuple of polynomials with n variables. And we're going to think of this as a map from Cn to Cn. Okay, and the assumption is that this map is injective. And the claim is that, in fact, it's also surjective. Okay, so this is something really special about polynomials. In particular, it's false for continuous maps. So if you a little challenge for you is to come up with a continuous map from Cn to Cn, or even your favorite incredibly nice and smooth map from Cn to Cn, which is injective but not surjective. It's not that hard. It's a fun little exercise. Okay, so let's do it. So can anyone suggest what to do? Does anyone have a guess as to what this what should go in this little red box? Yeah, finite, exactly right. So we're going to do this over finite fields. So first over finite fields, well, we have a map, and so suppose we have an injective map from fp to the n to fp to the n. Well, why is this surjective? It's surjective because an injective map from a finite set to itself has to be surjective. Okay, and now what do we do in general? What you do is you just reduce mod p. And then you have to argue something. So now you need to make a little algebraic geometry argument, which I'm not going to tell you the details of. You have to argue that surjectivity can be checked after reducing mod p for infinitely many p.
So we had a question about that the last time you did it.
Ah, great. So what's the question?
Basically, how does it follow from Nullstellen's sets?
I see. Yeah. So what you have to do is you have to, yeah. There's several ways of saying it. Maybe let me think if there's something that I can say that will be accessible. So what you want to show is that you have a map from a scheme to. Sorry, I can't say it in a simple way. You want to show that if you have a map from your finite type scheme to spec Z, it has constructible image. This is a really fancy way to say it. So if it has infinitely many closed points in the image, it hits the generic point. That's the fancy way to say it. Let me see if there's a simpler argument. maybe I was planning to avoid this issue, so maybe let me actually avoid it if that's okay.
That's fine with me.
Cool. Great. All right, so I claim that modulo this issue of checking something after reduction mod p for infinitely many p, we've solved the problem. And maybe it's a little subtle, so if you want to think about this, so the converse is not true. So if you have a surjective map from Cn to itself, it's not injective. So even though this first step would work. So you have to think a little bit about what kind of things you can check after reduction mod p. And my hint is that you can check the non-emptiness of a variety. So the non-emptiness of the set of solutions to a system of polynomial equations, but not that there's a unique solution. All right. Are there any questions about that? Great. All right, so we've talked about a lot of the algebraic geometry of C to the n, right? So we've talked about maps from C to the n to itself. So let's talk about what algebraic geometry is really about. It's not just about C to the n, about n tuples of complex numbers. It's about solutions to systems of polynomial equations. So suppose I'm given m equations and n unknowns. These are polynomial equations. Let me write that down. And then the set of solutions is called an affine algebraic variety. Over the complex numbers. You can also look over other fields, as we've already done. Okay, so you can ask a lot of questions about these, and I want to tell you about some of those questions, and again, how the answers are influenced by arithmetic. And maybe it's worth noting, I mean, there's this adjective affine here. So in general, algebraic geometers think about more general things, right? So they think about things built out of pieces that look like this. And those are more general varieties, like you might have heard of projective varieties, for example. All right, so here are some pictures of algebraic varieties. So this one is a cubic. So this is a cubic surface, and if you've heard about cubic surfaces before, you probably know that they have 27 lines on them, and this picture has the lines written on them. Right? This is a Kummer K3 surface. So at least some of these are. This looks kind of like a quartic. The solutions to a quartic polynomial in 3 variables. And then this one, if I remember correctly, is a quintic surface. So the set of solutions to a homogeneous degree 5 polynomial in 3 variables. Okay, so these things are awesome, and let's talk about them a little bit. All right, so one way we understand algebraic varieties is we think about families. So let me tell you what I mean by a family. So suppose I'm given just one polynomial, right? So one element of C adjoint x1 through xn, or even more than one if you'd like. You can think of that just like we were doing as a map from Cn to C, or in this case from Cn to Cm. And I've drawn a picture of this. And what we might be interested in this situation is what is the geometry of the fibers of this map. And that's something that can change. Like, so for example, here I've drawn one fiber is looking like maybe a nice quadric surface, like you've probably taught your Calc 3 students about. And here, this is a singular one, right? This is a quadric cone, right? And so here, this object degenerates to this one. Okay, so what are some kind of questions we can ask about these objects? So if you were really ambitious, and in my view, this question is ultimately the goal of algebraic geometry. Oh, and Andrew, sorry, asked if those were real pictures. Yeah, so those were the real points, the real solutions to those to certain cubic, quadratic, or cubic, quartic, and quintic equations. Okay, so what's the question that, in my view, underlies all of algebraic geometry? It's the following one. So classify all algebraic varieties / maps. Okay, I guess that's not a question, that's an imperative, but do that. But this is too hard. I mean, this is, I don't even know, like, how would you even make a well-stated version of this question? I don't think that's a reasonable ask. Okay, so let me try to make it more reasonable, and we'll go through a few stages of that. So one thing you could ask, instead of classifying a collection of objects, especially like a really fancy and scary one, is you could ask what's special about those objects. So in other words, can you give me a criterion that tells me that an object is not in this set. So it's not an algebraic variety or an algebraic map. So another way of asking that is what's special about varieties, so the sets of solutions to systems of all polynomial equations, or maybe maps between them, among like all spaces, for example, or continuous maps. So for example, how can you identify those spaces that show up as the set of solutions to a system of polynomial equations, or the set of continuous maps that are given by polynomials, or maybe locally by polynomials? All right, so let me just give you an example. So here's an example of a complex manifold, which cannot be written even locally as the set of solutions to a system of polynomial equations. So what you do is you take C2, you delete the origin. Well, now the group Z, the integers act on this by multiplication. So n acts by multiplication by 2 to the n, and I'm gonna take the quotient. So in other words, I'm going to identify a, b, two non-zero complex numbers with 2 to the n a, 2 to the n b for all n. So I've drawn kind of a picture of this. So this is kind of a two-dimensional picture, and you have to imagine a four-dimensional picture. But here I've drawn a fundamental domain for multiplication by 2 on set pairs of real numbers instead of complex numbers. So and what you do is you glue this ring to this ring and this ring and so on. So this looks like kind of a really wound up sphere or something. Okay, and the theorem, which is highly non-obvious, so I think the proofs I know of this go through Hodge theory, is that this Hopf surface is not a projective variety, which loosely speaking means it doesn't have a cover by affine algebraic varieties. You can't cut it into pieces, which are given by the set of solutions to a system of polynomial equations. Okay, so this is an example of a sort of very weak answer to our previous question. It's something that cannot be written as a variety. This tells you that varieties are a little bit special among, let's say, compact complex manifolds. Okay, so I told you this problem is too hard, and I've drawn a picture indicating how hard it is. So this is, my wife calls this a wiggly alien tofu. So what do you do when a problem is too hard? You linearize it, if you're in calculus, or maybe you might take its say that's taking its derivative. So we're going to take the derivative of our really hard problem, and so we're going to turn it into a problem of linear algebra. So let me say what I mean by that. So what I mean by that is I'm going to try to understand what happens, like how do the linear algebraic invariants of let's say I have a map, and I want to understand what are the special structures on the linear algebraic invariants of these objects. So let me tell you what I mean by that. So suppose I have, for example, a loop upstairs. So this is a loop maybe in one of the fibers of a map between two algebraic varieties. And I can take a loop downstairs too. And what I'm going to try to do is take my loop upstairs and drag it in some path over the loop I drew downstairs. And when I do that, that's something I can do. When I do that, I might come back to a different loop than where I started at. And this is the kind of thing that I'm going to try to formalize in the next slide. Okay, so formally, what do we do? So let's say we have our space. So this was the target of a map from y to x. So maybe you can think this is for example the complex numbers minus some points. Although I've drawn this to indicate that it might have a little bit of topology also. And I take a base point. Then what one can study is the fundamental group of this space. And what that does is it captures the geometry of loops. So what is this? This is loops based at x up to homotopy, so up to deformation. So what this means, for example, is that I view this loop as the same as this loop, just because I can wiggle one and get the other. And this has some algebraic structure. It's a group. If I have two loops, I can go get a third just by going around one and then going around the other. Okay, and how do I undo a loop? If I have a loop, I can invert it just by going along it backwards. And well, that's not literally the constant loop, but you can deform it to the constant loop. All right, so this is one kind of linear algebraic invariant, or at least group theoretic invariant of an algebraic variety, or really a space in general. It's loops at X based up to homotopy. Okay, the other interesting invariant that people study, so the other way of linearizing a space or a variety, is the cohomology or homology. And I'm not going to define it precisely, but what it's supposed to do is it's supposed to capture a more free notion of deformation. So for example, if you have a loop over here and a loop over here, these don't have any points in common. We're not taking a based homotopy, but they're both the boundary of a tube. Okay, and you could do the same thing with higher dimensional things. Instead of loops, you might take spheres, for example. So what cohomology is it's
Daniel,
well,
are the loops in your Pi1, are they like real one-dimensional loops? Or
yeah, exactly.
Okay.
Real, it's the normal notion of a loop, like literally drawing a loop.
Okay.
Almost. Yeah, exactly right. So in other words, they're maps from the circle, continuous maps from the circle into your space. All right, so here what we're going to do is, well, I'm gonna tell you a slight lie. So this is what I'm going to write is this is cocycles modulo co-boundaries. But really what you can think of it as is cycles mod boundaries. So meaning you're taking things like a loop or maybe even a surface or a collection of such things, and you're saying that such things are zero if they're the boundary of something else. So in other words, what am I saying here? If I have these two loops, they're the same if they're the boundary of something else. So that's a little bit of a lie because of these words co, but don't worry about it. Okay, and I told you
this singular cohomology here. You
Yeah,
just
this is gonna be-
topological.
This
Totally
is a singular cohomology of a fiber of a map. So the situation we're in is we have y to x, we have a point x and x, and I'm going to take the fiber and take its singular cohomology. That's exactly right. That's a good question. All right. So what's our linearization of a map? So suppose I'm in this situation, I have a map from y to x, I want to linearize it. I want to get some information about it that we can understand in a more linear algebraic way. So what it is it's going to be an action of the loops in the base, based at our base point. So this is a very geometric object. We take loops, we take them up to homotopy, and we're allowed to compose them. And I claim that this is going to act on this object. What I think, sorry, was that Benjamin who asked about the singular cohomology? What Benjamin called the singular cohomology of the fiber over our base point. Okay, so this is a complicated object, but what is it formalizing? It's formalizing this intuition I drew over here. Namely, if I take a cycle upstairs, if I take a loop, and I drag it around through the fibers over the loop over the space, then maybe I get back to somewhere else different from where I started. Okay. If you've seen the theory of, if you've seen multi-valued functions, you'll have like for example, the logarithm, you've already seen an example of this, right? So if you take a logarithm, that's defined away from a branch cut, right? And if you travel in the complex plane around the origin, you get back to somewhere different from where you started. And that's exactly an example of this. That's the case where instead of having a cycle up here, a one cycle, a loop, where you just have a point. Okay, and this is a big generalization of that. If you've studied differential equations and seen the situations where you've multi-valued solutions to differential equations, this is really a version of that. These families of loops are in many situations, they correspond to solutions to certain differential equations. All right, so I claim the linearization of a map is a linear algebra gadget. It's a representation of loops in the base, pi1, on the cohomology of a fiber. So here's a version of our question from before. It's which actions like this, or which representations, show up from maps of algebraic varieties.
And that cohomology is a vector space, right? So this is like literally a representation in the sense of like representation theory.
Yeah, so if I, instead of putting Z there, I'd put Q or another field, it would be a vector space. That's exactly right. I put Z there, so it's just an abelian group.
Okay.
Yeah, so if you'd like, you lose very little by putting Q here. And then this is literally a representation of a group. Okay, and maybe let me just remark, so I asked this question, which actions or representations show up like this from maps of algebraic varieties? It's not obvious that there's any restriction at all. Like in fact, for topological spaces, it's not too hard to see. You can get any representation like this show up. If X is an arbitrary space and Y is an arbitrary space allowed to map to it. You even can do it with manifolds if you work a little bit. So the so here's the question. So what is special about algebraic varieties? One way of asking that is what is special about these representations? And I want to explain to you how we get some restrictions coming from number theory. So here's a result of, well, it was proven by lots of different people. It was proven by Griffiths and Landman, and then the most general version, it was proven by Grothendieck. So Griffiths and Landman proved complex analytic versions of the statement, and then Grothendieck proved it in general. So suppose you have the simplest kind of loop. So suppose this is just we took a one-dimensional complex manifold, so a Riemann surface, and we punctured it at one point. So here I've drawn a little local picture. You can think maybe this is a little piece of the complex numbers, and I've deleted one point. And suppose I take a little loop just around that one point. So this is the simplest example of a loop that you can't crush down to zero. Why can't you crush it down to zero? It's because it goes around this puncture. It has non-trivial winding number, right? So you can ask, what if you have a loop like this? How does it act on these abelian groups, or how does it act on these vector spaces? Maybe let me just be safe. Let me put a Q here, just like Brian asked for. Well, okay, so this is the last time I gave a talk involving this theorem, everyone logged off when I said this word. So don't be scared, I'll explain what it means. This theorem is that this action is quasi-unipotent. Okay, and all that means is this thing is a matrix. It's a map from a vector space to itself, and that matrix has some special properties. What are they? It means its eigenvalues are roots of unity. Okay, so this is an incredibly special matrix. Like most matrices don't have eigenvalues, which are roots of unity. So what is this saying? So for example, imagine that I had a map. So here this is X. I have a map Y to X. Imagine X was just the complex plane minus a point, right? So then well, there's only one interesting loop. It's the loop around that point, and it's saying, well, how does that loop act on the cohomology of a variety? Well, in the topological world, it could be literally any matrix, right? You could take any n by n matrix with rational coefficients. But here we're saying it can't be any matrix. It really has to be very special. It has to have roots of unity as its eigenvalues. Okay, and the thing I want to convey to you for basically the rest of the talk is why that's true. So I want to say that this is coming from number theory. So what's the idea of the proof? Well, just like before, we have our map of varieties over the complex numbers. Well, these varieties are defined by a finite set of polynomials with finitely many coefficients, and so is the map between them. So all we have to do is take the same situation over the ring Z adjoining the complex numbers. All right, so this is an arithmetically interesting ring. If you'd like, we can even take a field. We can take Q adjoining the coefficients. And let me call that field K. All right, so Grothendieck's amazing innovation is to replace all the objects in this picture with algebraic versions. So he comes up with an algebraic version of pi1. He comes up with an algebraic version of cohomology. And these algebraic versions are very special in that they actually come with a Galois action. So the automorphism group of the algebraic closure of this field acts on them. So we get an action of the Galois group of this field on both of these objects. And the incredible feature of this is that the action of pi1, so this a priori unconstrained linearization of the map we were studying, is in fact equivariant for these actions. So it's compatible with them. Okay, so let me just tell you what the key case is. So the key case is where we think about the situation where our loop around, where we have a loop around a puncture. So this is our loop around a puncture that we're interested in studying. And suppose we have another element, sigma, acting on it. So when we conjugate tau by sigma, we get tau to some power. And you're supposed to think sigma here is in the Galois group of this interesting field wherever. Then I claim that if we have any representation of this group, tau is forced to be quasi-unipotent. So the eigenvalues of tau are going to be roots of unity. So let me prove that. So suppose lambda is a tau eigenvalue. Well, tau to the q is conjugate to tau, right? So they have to have the same eigenvalues. So this tells you that lambda to the q is also a tau eigenvalue, right? So that means that lambda and lambda to the q and lambda to the q squared and lambda to the q cubed and so on are all eigenvalues. But a matrix can only have finitely many eigenvalues, right? So lambda is a root of unity. So we proved it. Okay, modulo the very hard work of defining these algebraic variants of the objects we were studying. Okay, finally, I want to tell you about a couple things I've done using this method, which I'm really proud of. So the thing we were interested in studying is maps from y to x, and I want to tell you about some restrictions on these representations. So some things that are special about them when these maps come from geometry, when they're defined by polynomials. So first of all, suppose I have a map like this. So suppose I have a representation of the fundamental group, which comes from geometry. And suppose when you reduce it mod some big number, it's trivial. Okay? Then here's something you can prove. It's in fact trivial already. So what this is saying is you can check if the action if one of these representations is trivial by reducing mod a billion, for example. Okay, and then there's some interesting uniformity. A billion here only depends on the base variety x. It doesn't depend on the family you started with. And this is totally explicit. So for example, if the variety you started with was, so what is this? This is the complex numbers minus 0 and 1. So this is the first interesting example of a variety with a non-abelian fundamental group. Then you can do this for any, you can reduce mod m for any m at least 12. Okay, so that's something you can check. Oh, and Jason asked, what does come from geometry mean? So comes from geometry means arises from the singular cohomology of a smooth proper map of algebraic varieties. Thank you, Jason. Yeah. So it means that it arises in this way we've been discussing. So it's one of these linearizations of an algebraic map. Are there any questions about this?
Ken asked one before about tau, which by the way, you wrote tau. So tau doesn't have to generate the whole group?
That's exactly right. Yeah. So this is saying anytime you have a curve and you delete a point and you take a little loop around that point, then it always has to root of unity eigenvalues. Yeah. It's really incredible. It's like a universal fact about all representations.
And I took a class with Fernando Rodriguez Villegas many years ago, and he said that every 12 that ever appears is like platonically the same 12.
So this is a different
I'm sure
12.
That's the same 12.
This is a different 12, unfortunately. So it's really you just need to look at prime by prime, and you need the 2 part of your number to be bigger than 4, and the 3 part to be bigger than 3. So for example, you could also reduce mod 5, and it would still be true. This is just a slightly simpler statement. All right, so let me briefly tell you the proof. So the proof idea is the same as before. So you study the Galois action on pi1. All right, so I'm almost out of time. So let me just tell you one more theorem. So I think I really love this theorem because it tells you that these representations are actually really special. So we asked before, like which representations can come from geometry or which maps can come from geometry. It's not even obvious that there's any restrictions at all, although I've already told you some, like Grothendieck's local monodromy theorem. So here's a theorem. Suppose I have a smooth variety and okay, a finite extension of QP, just think a field. Then the theorem is that that if you look at the set of representations into GLN with coefficients in this field, which come from geometry, it's finite up to isomorphism, up to conjugacy. So this says that representations which come from geometry are extremely special. So there's only finitely many of them of each rank. Okay, and maybe just a couple brief remarks. So Deligne proved this over Q. So if you replace this L-adic field with Q using analytic techniques. So here this theorem implies Boolean's theorem, but it also works over, for example, in positive characteristic with a couple extra adjectives. And then maybe finally, I just want to mention the really cool thing this is a consequence of is that the set of representations into QP bar, whatever that is, that's some big field, is topologically discrete. Okay, and I mean this is a hard theorem. I mean, so it takes as input, for example, the pieces of the Langlands program. But nonetheless, the fundamental idea is that you're looking at these complex varieties. They have finitely many coefficients, and then you use that finiteness to get yourself into an arithmetic situation where you can take input from number theory. Okay, so that's all I wanted to say. So here's plus and times again, and now hopefully you feel like I can add you here also, holding their hand. So the goal was to sort of help you guys become friends with polynomials and also show you some of the sort of ridiculous interactions they allow between number theory and geometry. And so I hope that was successful. And that's all I wanted to say. So thank you guys for listening, and I hope you're friends with the tofu and the cartwheeling operators.
We do have a few minutes for questions, and Kim had a nice one. That two, we often have to throw away two, but Kim, do you want to ask the question?
So in this theorem, so what happens at 2 and 3?
Well, I'm used to seeing conditions where you need a certain amount of 2 before something starts behaving, but seeing 3 be required up to a certain amount is surprising to me. What happened to 3?
That's a good question. So I think probably the truth is not 12. Probably the truth is 2, actually. I think it's probably an artifact of the proof. I mean, the proof involves a fine analysis of the Galois action on the fundamental group of P1 minus 3 points, which is like actually a really mysterious object. So Milne calls the fundamental group of P1 minus 3 points the most interesting object in mathematics, which is maybe a little hyperbolic, but it's I think it's a cool object. The point is it's a mystery, and so if you want to prove the best possible versions of the theorem, you have to know, you have to sort of know way more than human beings know about the Galois actions on these fundamental groups. So 12 is what I was able to prove. It's not, it's probably not the truth. Yeah, but the proof goes by a kind of prime by prime analysis and for any variety. And then what will happen is you'll see some finite number of bad primes, and then for large primes, like the prime itself will work. And that's somehow where this comes from.
Other questions?
I ask a terrible question. Does any of this machinery kind of translate to the case of non-algebraically closed fields?
That's a good question. So I mean, ultimately the proofs pass through non-algebraically closed fields, right? So the idea is to get oneself in a situation where you have an interesting Galois action, which is of course only in the non-algebraically closed case, and then you prove something there. So there's in each of these proofs, there's a stronger theorem about varieties over non-algebraically closed fields, but stating it would be too complicated for today.
Okay.
That's a good question.
Ben asked earlier that your hop example that isn't a variety, is it compact?
Yeah, it's a compact complex manifold.
Okay.
Yeah, so you can see, for example, I mean, I sort of drew the real picture, but you can see a fundamental domain is kind of annulus, which is compact.
Mm. And we had one earlier. We had a talk from Michelle a number of weeks ago. It was titled something like "Period 3 implies chaos."
Oh yeah.
And so there was a connection earlier on when you were sort of, I think, to your fixed point kind of things. Is there a connection to that idea?
Oh, I see. I don't think so. So this fixed point result I stated only for an involution, but it's actually true in the same proof works as long as f has prime power order. So for example, it's true if f composed with f is the identity instead of f composed with f. So there, well, okay, there would be one small change in the proof. Instead of looking over instead of looking here at an odd prime, you'd look at a prime which doesn't divide the order of f, right? So if you had f of order 3, you'd be fine as long as p is not 3. Yeah. Yeah, so I don't think, I mean, somehow there are interesting things that happen with polynomials of composite order, but I think it's not something special about 2, if that's what the question is.
Mhm.
So you mentioned this conjecture about involutions, that every polynomial involution is conjugate to a linear one.
I think it's even conjectured to be true for arbitrary finite order polynomial automorphisms.
Oh wow.
I don't know.
Okay.
Sorry,
I assume that people
shouldn't say
expect
it's a
that the
conjecture,
answer
it's a
is. What's that?
I shouldn't say it's a conjecture. It's a question.
Because I was going to say, I assume people expect the answer to be that it's true, that everyone is conjugate to one of those.
I think it depends on who you ask. I know of at least one person who does not expect that.
Okay.
My guess is that that's the most common.
I see.
If that's true, it makes this theorem a little less exciting, but because for something that's conjugate to a linear map, it's very easy.
I see, but nobody's been able to write one down. I mean,
That's
it
right.
seems like, well, okay.
I believe in positive.
It captured my imagination.
Yeah, I think in positive characteristic, if I remember correctly, there are finite order automorphisms of affine space which are known and are not conjugate to affine linear ones. But I think in characteristic 0, it's open. And I think we don't have an example of order 2 in any characteristic, if I remember correctly. But I'm not an expert on this, so don't quote me.
Do we know that in at least low dimensions like C2?
I think we know essentially everything about automorphisms of C2. I would have to check if we know this, but I think we do.
Yeah, I mean, usually these things follow from Young van der Kolk, right?
Yeah, the person to ask is there's this guy Krantz, who has like 1 million papers on finite order automorphisms of affine space, which are very good. I read a couple of them as I was prepping this talk, actually.
Well, as we wrap up, we want to make sure that we advertise next week's talk. It's from Lauren Siegel. The title is Mathematics Outside of School, Why We Need It. Lauren is from the Math Happens Foundation. So we're going to be talking about math running wild out in nature and things. So I hope you all join us. Will everyone else join me in thanking Daniel one more time? All right. We can linger for a minute or two.